Okay, so we have a couple of minutes before the official class start time. Does anyone have any questions for me? All right, so today we're going to take a look at an implementation or a couple of implementations of priority queues. So far we've been looking at data structures, well, the data structures that you usually implement as binary search trees or skip lists. So those are sometimes called dictionary data structures or successor data structures. But there's a whole different sort of class of classic data structures, which is these priority queues. And I'm sure that all of you have seen them before. The main thing about them is, well, usually they store a set of data which can be ordered in some way, so it's totally ordered. So if you, in particular, if you ask me to point out the minimum of the set, that's a well-defined thing and it's unique. So that's just like what binary search trees do, but they don't support all the same operations. So you can always add something to the set, just like in binary search trees. Priority queues care about keeping track of the minimum. So they seem to be interested in that kind of thing. So there's a find min operation, which tells you the minimum value in the set. And then there's a remove operation to remove things from the set. But you don't get to say what is to be removed. It's always the minimum value that gets removed. Okay? And there's variants of these that support, let's say, more of these operations, some extra list of operations here. But these are the sort of core things that define priority queues. In particular, you don't get to choose what to remove. That makes a significant difference. And you can't go searching in a priority queue for some particular value to know if it's there or not, or you can't search for some value to find some other value that's close to it. Really, they're focused on keeping track of the min. So compare these to a similar structure, which is the queue, which or a FIFO queue. So those things, you can also add stuff to a queue, and you can remove stuff. But what gets removed from a queue is not the smallest thing in the queue. It's whatever the oldest thing in the queue was. So whatever has been in the queue the longest, that's the next thing that gets removed. Okay. And queue, I guess, is a British term, because that's how British people talk about what we say standing in line for something. You join the back of the line when you're added to the line, and the front of the line is the next thing that leaves. So these are really easy. Lots of ways you can do this. You can use a doubly linked list. You can even use a singly linked list, as long as you join out at the correct end and remove from the correct end. And you can also use a dynamic array. So an array that grows and shrinks when necessary, along with a few possible tricks. Modular arithmetic is probably the most common one for implementing a queue. These ones, I'm sure you've seen implementations before. The usual implementation that you see is the binary heap. And that is the most common implementation, is a perfectly balanced binary tree. So every level has as many nodes as possible, except for the bottom level, and even the bottom level packs all of the nodes into the leftmost children, so as far left as possible. Well, it has this heap property that we've seen in this course when we looked at Queaps. The minimum value goes at the root, and then I don't care what goes left and what goes right, but recursively, the minimum value in the left subtree should be here. The minimum value in the right subtree should be here. And these things are, well, I'm sure you've seen them. They're easy to implement. Find min is trivial. It runs in constant time because you just return the value that's stored at the root. Add is not as trivial, but not difficult. The thing that you're going to add means you're going to add a new node to the tree. Where is that node going to go? Well, it's going to go at the leftmost available position in the bottom level. So you attach it there. You put the new value you're adding there. And then you may have an issue that this thing is smaller than its parent, in which case you swap it and its parent. And you may have to do that until you reach the root. So similar to what we did with Queaps, except all you have to do is swap the values. You don't have to do any rotations. And all of this actually, because this is such this is a perfectly balanced binary tree with all the leaves packed to the left, you can actually implement the whole thing in a single array. You don't explicitly store the tree. All right. So that add operation then runs in O of log n time, because all you do is insert the next leaf. That takes constant time, and then you have to do this bubbling up of this thing while its priority is smaller than that of its parent. You move it up. That takes at most log n steps. And why is that? Well, that's just because this thing is perfectly balanced. So you have some inequality, like the number of nodes is at least 2 to the height of this thing. And removing the min is also kind of easy. You just take the min out of the root. You then take the last node down here, take its value and stick it up in the root. The node goes away. And now you have an issue that this thing may be larger than one of its 2 children. If that's the case, you take the smaller of the 2 children and swap those 2. Okay. So, and at each stage then, you have sort of a 3-way tournament between this value, and this value. The smallest of the ones wins the tournament and goes to the root. The other one moves down, and then you do another 3-way tournament until eventually this thing doesn't need to move. Again, that's only there's only log n levels. Each time you do that, the depth of this thing increases. There's only log n levels, so that's also going to be of log n time. Yep. Well, because at least for the binary heap, you want the tree to have exactly this structure. So the shape of the tree is completely determined by the number of nodes. So that means you want them packed to the left. And so if I just did something like take the min away and then look at these 2 to decide which one is going to go there, well, it could be that this is the smaller of the 2, so it goes there. Okay, so, and then I can continue this way, but you can see what's going to happen is eventually that's going to leave a hole in this subtree. There'll be a leaf missing, and then it doesn't have this beautiful shape that we want. So you force the last one here to be the one that goes to the root. It's by far not the only implementation of a heap as a binary tree. It's just the classic one. It's the one that everyone teaches and a lot of people use. If you want an alternative implementation, we've seen one already. It's called a heater. And it's just the inverse of a tree. So it's kind of the same thing as a tree. Remember, a tree, we wanted to implement a binary search tree, and the way we did that was somebody gives you the keys to insert. They want to insert, remove, and search for in the tree, and whenever you insert a new key, you give it a random priority. If you go the other way around, if somebody gives you priorities that they want to insert, then each time you get a priority, you assign it a random key. And well, the same thing happens. That means that if you were to sort the keys by their priority, you get a random permutation. The tree that you get looks like the random binary search tree that you get from random permutation. It's the length of a search path is logarithmic in expectation, so everything just works exactly the same. So for the same thing, in that case, the smallest priority is at the root. So find min will take constant time. Adding something is the same algorithm as adding in a tree. You assign a random key. When you get this priority, you search for the random key in the tree, you attach it at that location, and then do rotations to adjust the priority. Yeah.
This kind of structure, we always put the data items at the last level.
No, the data in a binary heap is stored in every node, and the same thing in.
Okay, so when you were like drawing that tree, you said that each node kind of stores the minimum value of the next subtree.
No. It stores this node up here stores the minimum value in the entire set, and this is the only place that value is stored. Okay. So there's exactly one node per item in your set of priorities.
One more thing about the AND operation. So when you add something, you do log n like comparisons to make sure it's in the right place.
Yeah.
So for a tree, you showed that could be done in constant time. That also apply here or not?
No, because in a tree, there's two things that you have to do. One of them is you have to find the location where you want to add it, and the other is to do some rotations to adjust the priorities. Finding the right location still takes log n time, because that starts from the root and works until it finds it. So there's no shortcuts there. All right. And one of the things that you may have seen, one application of heaps, in fact, usually when you teach these in an intro data structures course, you teach binary heaps, and then you teach the Heapsort algorithm. And what's the Heapsort algorithm? So you're given n items you want to sort. You build a heap out of those n items using those n items. And then you repeatedly call remove min to take the smallest one. That's the first one in sorted order. And then we call it again, you'll get the second smallest one. Call it again, you get the third smallest one, and so on. And Heapsort is just a quick, it's a slightly optimized implementation of that idea of just insert n values into a heap, or priority queue if you don't want to be specific about what kind of priority queue, and then call remove min n times to get the values in sorted order. Okay, and Heapsort's a nice, elegant implementation of that, where you can manage to do the whole thing using only one array of length n. All right, so one of the things that seems to come up a lot, and we kind of made it come up last class when we looked at data compression, is that sometimes, I mean, some instances of problems are easier than others, and some instances are more difficult than others. So we saw, for example, that data compression is kind of easy when you keep seeing the same letter repeatedly in a whole bunch of positions in a row. And we tried to, the Burrows-Wheeler transform that was the last thing we looked at, is just an attempt to try and make that happen as often as possible. And sometimes, in the real world, you just get lucky, and the data that you want is, the data looks, does something good for you, and you like to take advantage of it. People in the data structures world call these adaptive data structures. In the algorithms world, they might call them instance optimal algorithms. But all that to say, in the world of people who study sorting algorithms, people are interested in algorithms that run fast on things you're likely to encounter in the real world. And one of the things you're likely to encounter in the real world is data that's already sorted, or nearly already sorted, because it just tends to happen. In fact, it just tends to happen that you pull things from some database, they come out in sorted order, you mess with them a little bit, and then you want them in sorted order. So you call a sorting algorithm, which really doesn't have to do much work. Unfortunately, if the sorting algorithm you use is Heapsort, well, the fact that the data is in sorted order to begin with doesn't really save you, doesn't necessarily save you anything. All right, so there's a pseudo motivation for what I'm about to talk about now. And so let's actually think about what that means in terms of heap sort. Heap sort, if you give me run heap sort, this sort of dumb version of it on an already sorted list. So you go through the list and you take the values one at a time and you insert them into the heap in the order that you encounter them, which is sorted order. And then you call remove min n times. Well, the first thing that you gets returned by remove min will be the first thing that you inserted. And the second thing that gets returned by remove min will be the second thing that you inserted, and so on. So in that case, actually, you didn't need a heap. A queue does that. And queues, they do these operations in constant time. So somehow we'd like to mix a heap so that we get things in sorted order, but if we get lucky somehow and things seem to come out, things went in already in sorted order, you'd like them to like that to be faster somehow, so it behaves more like a queue. So last class we saw the working set number, which roughly speaking was the number of distinct items accessed since the last access to X. We'd like to define something similar for priority queues, but and it's not about things that were more recently accessed, but basically things that were added a long time ago. So this, if you think of it in terms of whether it's first in, first out, or last in, first out, this is a little bit more like a stack. So, right, if you access something and you move it to the top of the stack each time, then this thing really is the position of that thing on the stack. In fact, that's what the move to front compression algorithm does. We're interested in more the opposite thing, that if I inserted something a long time ago, and all the things that I inserted before it are already gone, then it should be somehow ready to go. So that defines this thing, which it's called the QNumber of some value. And it has to do, it's for these priority queues. So the QNumber of X is just equal to the number of items added before X that are still in the priority queue. Okay. So if you think of this thing really as imagine you have this queue view. A bunch of things are added. Let's say these are added. Then you add X. You add some more things after X. And in the meantime, some things leave. Not necessarily in some order, in this order. And now I ask you, what is the Q number of X? Well, it's the number of these things that were added before X, but haven't left yet. So in this case, the Q number is, Q number of X is 3. And if you think about what happens when you you use heap sort on a sorted array, then the Q number of the thing that you're removing is always 0. Okay. So the first one that you insert Well, it's the first one that you insert, so nothing is inserted before it. So nothing was inserted before this smallest one. So that means that makes it 0 for the first one. For the second one, only one thing was inserted before it. It was the smallest thing. But by the time you want to remove the second one, you've already removed the smallest one, the first one. So this seems to capture the idea that's like the inverse of this thing. So if this was last in, first out, then this is somehow represents first in, first out. And what we would like is a data structure that gives the following bounds. I want to be able to insert in constant time. I want to be able to find the minimum in constant time, so at least as good as these things. And I want to be able to remove the minimum in O of log of Q of the minimum time. So when I remove the minimum, I look at how many items are in the queue that were inserted before the minimum, and I want to be able to do it and log that number. So this is certainly not more than log n, but could it be much smaller? It could be, well, log of 0. Okay. And besides this Heapsort sort of motivation, there's lots of sort of real world situations that you can imagine where in general the discipline, what happens is things are processed, the first one to come in is the first one to come out, except in a few special circumstances. So think of, so I went to Canada's Wonderland with my kids this summer. And of course, the lines for the rides are it's a queue. I mean, you want to get on the ride, you go and you join the back of the line. You wait until everybody who's in the line before you gets to do their ride, and then you get to get on the ride. Except if you pay $150 and buy a fast pass, a very small number of people do that, and those people just arrive and they skip straight to the front of they enter the fast pass line. Okay. So if you imagine processing this thing, being the data structure that processes some sequence like this, and this isn't, I mean, it seems weird to talk about this at Canada's Wonderland, but in network applications, there is exactly this happening. There are certain classes of network traffic which are just higher priority than other classes. So in general, things are first in, first out, but a few high priority things come through. Then you see that like 99.9% of the things that come out are basically first in, first out, with a small fraction of things which jump ahead in this queue. Okay. So let's see how we can do this. Does anybody have an idea how this might happen? Probably like nothing you've seen before. Okay. That's okay if you don't even have a clue. And it's probably like nothing you've seen before, because there seems to be two things that we're trying to do. We're trying to maintain order according to a queue, but we're also trying to maintain some partial order according to these priorities. And it's really not a sort of natural thing to do, and it doesn't come up or it hasn't come up in probably any data structures you've seen. Yeah. Mm-hmm. So we have a problem. There's a problem with that, which is that it uses hash tables, and hash tables don't really respect anything about ordering. So in hash tables, you can always find things exactly, but there's no notion of finding the smallest thing or finding something close to something else. That doesn't really do it. You can imagine for some of the situations that the sort of examples that I described, in particular the network application or even the fast passes at Wonderland. Well, Wonderland has a system for this, of course. What they do is they just have two separate lines. In fact, now I think it's even up to 3 separate lines. There's the cattle who live in the longest line. There's the fast pass people. And then I think there's a fast pass plus or something that lets you even jump ahead of the fast pass people, which I always like to see happen. So for them, it's easy. They only have 3 categories, 3 priorities. So they just maintain 3 different data structures. But that's not going to work for us because our priorities are an arbitrarily large set. Something silly you can try is, I mean, how bad is it if you just try and use a queue, right? So things come in at this end, and well, they get to leave from anywhere, but you search for them in some way. So I don't know, the priorities are added over here. So adding something to this list takes constant time. Find min, well, you could try to hack that in some way and say, well, one way to deal with find min is the same way that it's dealt with in heaps, which is you just maintain an explicit pointer to whatever thing happens to be the minimum. Then I can tell you the min in constant time. And add works fine with that, because when I add something new, I can check to see if it's smaller than the current min and then update the current min if necessary. So these 2 operations, they're easy to do, and this works. But what about this remove min? Well, remove min wants to remove this thing. And okay. So yeah, that's easy to do. Cut it out and remove it. But what's the problem now? Now we don't know what the new min is. And if this is all we're maintaining, not only do we not know what the new min is, but we don't even have an idea where to look. So one thing that could have been useful is if we knew at least whether we need to look for the new min somewhere else. I mean, it would have been nice to know whether we could find the min here or whether we have to look here, or maybe we don't have to. So you can actually cook something up fairly easily, which has everybody pointing to the smallest value which comes before them. I don't know, maybe something like this. And then if you do that just right, that means when I delete the min, I will know the smallest value in the front half, because the front part, because this pointer that was stored here points to that smallest value. And so the only thing I would need to update is this. That's good, because the number of things here is exactly the Q number of the min, right? These are things that were inserted before the min and are still in the queue. So that would be good. Problem is, we want the log of the Q number of the minimum, not Q number of the minimum. So we can't just scan this whole thing. Okay, so there's a fairly okay, so if everybody has a pointer to the smallest thing that appears before them, you get some pointers that maybe look like this. Okay, so maybe this is the smallest one overall, and then, so then maybe that guy points to there. And I forget. So when you add something new, what happens to these pointers is this could be smaller than a bunch of stuff here. So that would involve updating a whole bunch of things to point to this. And there is a clever way to do that. It's done in minqueues, but I forget what it is now. So there's sort of an old classic way of doing that. I forget the trick now, but that's okay. The bigger issue is well, somehow you still don't know where the new min is after deleting things. You know what the minimum is up to the thing you're deleting, but you don't know what's coming after. All right. Pardon? The time to find the min, yes. There's a thing called a minqueue that you can add and remove things in constant time. I forgot what the trick is now, but it's a fairly easy amortization. It's a fairly easy thing. Okay, so we're going to have to do something, and it's going to be different than what we've seen. So we're going to need a couple of tricks. One of them, if you've taken data structures with me, you've seen before, and it's called the 2-4 tree. And don't worry, it's actually it's a really easy thing. So a 2-4 tree is just a tree in which every node that is not a leaf, so every internal node has 2, 3, or 4 children. That's one rule, and every leaf has the same depth. Okay. So here is an example of a 2-4 tree. See that it satisfies these rules. Internal nodes, 4 children, 2 children, 3 children, 2 children, 3 children. Satisfies the first rule. Every leaf should have the same depth. Here are all the leaves. They all have depth 1, 2. So that's a 2-4 tree. And an important property of a 2-4 tree, I'll write it down here. A 2-4 tree of height h has at least 2 to the h leaves. Why is that? Well, a 2-4 tree of height 0 is just a single node. It has 2 to the 0 is one leaf. It has the root. A 2-4 tree of height 1 is just this root and its children. How many children are there? 2, 3, or 4. So that's always more than 2 to the 1, which is 2. And in general, the number of nodes at depth I is going to be at least 2 to the I, which means the number of nodes at depth H is going to be 2 to the H. So these 2-4 trees, they always, they get bushy really fast. Another way to think about that is if instead of H, you think of, well, if you have n leaves here, then how big can the height be? It means that the height is at most log n. So 2 to the H is less than or equal to n. All right, so that's one thing about them. One that you've seen if you've looked at them before, but another important thing that you may not have seen is the following. Given a pointer to a leaf, let's say V, we can remove V or add another leaf beside V in constant amortized time. All right, I'll quickly explain this part because most of you will not have seen it before. So it says, and let's look at some example like this. It says if you give me a pointer to some leaf V, like here, then I can either remove V or add a leaf next to V and constant time, constant amortized time. So first I'll show you the algorithm. You won't believe that it runs in constant time, and then we'll analyze it more carefully. So first, to add something adjacent to V, you do the obvious thing. So I want to put another leaf in beside this V here. Well, you make that thing a child of V's parent, and you make it the, right in between V and the thing that came before it, or just before V. So what's the problem here? Pardon? Yeah. So the problem here is this is no longer a 2-4 tree. In particular, this thing, its number of children increased by 1, which means that it could now be more than 4. It could be 5. So that can happen, in which case you take this thing and you split it into 2. And one of these 2 nodes gets 3 of the children, and the other one gets 2 of the children. Now, there used to be only 1 node here. Now there's 2, which means that the parent of that former node should have both of those things as children. What's the problem? Same thing. The parent of this node that I split, its number of children increased by 1, so now potentially it's 5, which we're not allowed to do, but we know how to deal with that. We split. So we take this thing and we split it into 2. One of them gets 3 children, the other one gets 2 children. And this used to be only one node, which was only one child of its parent. So now its parent needs to have 2 children. Any problem now? Can you foresee a difficulty where there could be a real major problem? Yeah, so one thing you might think is, but that's not so good. What if the root already had 4 children? So that would have looked like this picture. Then you have to split the root, which you do. And now you say, well, okay, but I'm only allowed to have one root, and now I seem to have 2 of them. What do? I just make a new root that has these 2 nodes as its children. And now you can check, okay, that definitely it stops now. This node only has 2 children, so it's over. Every node has 2, 3, or 4 children, and miraculously, every leaf still has the same depth. The depth of every leaf increased, but they all increased at the same time, so that's okay. So that's fine. So for insertion, you basically just make the node a child of the appropriate parent. If that thing now has 5 children, you split it, and repeat that until you stop. Yeah. What's the content of? Okay, so for now, don't worry what we're going to store here. We'll see for this application, we're going to store something different, but just think about the shape and inserting leaves at particular locations. So that's how you insert. And removing, well, you do the obvious thing. I mean, here's an example. Let's say I want to do something real simple. Where's a good example? Here. So let's say I say I want you now to remove this node. This is the leaf V that I want you to remove. So you just remove it. The only effect that has is that the parent of that node now has 1 less child. And potentially that means that the parent only has 1 child, and that is not allowed because it has to have 2, 3, or 4 children. If that happens, you do one of 2 things. You look at the neighbor of this guy. So the neighbor of this guy is the sort of the sibling. So the next one in this order. And if that one has more than 2 children, then you're happy, you just borrow one of its children. You adopt one of its children. That's what happens here. So if that one had more than 2, then you can adopt one, and now you each have, this one now has 2, and that one still has at least 2. That's good. Sometimes that doesn't work. Like, for example, if I delete this, I ask my sibling if I can borrow one of their children, adopt one of their children. The sibling says, no, I only have 2, and I need to have at least 2. So what happens is you take those 2 nodes. So that means together, you have a total of 3 children, these 2 nodes. 1 in this one, which is what we're trying to fix, and 2 in this one, because it has to be 2 because there's nothing to borrow. So that's 3 in total. And so you merge those 2 into a single node that has 3 children. And now that may trickle up to the parent because the parent now has 1 less node than 1 less child than before. In this case, it does trickle up to the parent. And This one tries to borrow from its sibling. That's not possible because the sibling only has 2. So you merge those. And then the number of children at the parent goes down. In this case, it stops here. And again, this can go all the way up to the root, in which case you have a root that has only 1 child, and you remove just take the root away. And the height of the tree decreases by 1, but everything continues to work. All right, so there's a strange claim on the board that says you can do this in constant amortized time. And what I just showed you points to log n time, because you make a change at the root and it trickles all the way up at the leaf, and it trickles all the way up to the root. So how is that going to be constant time? It definitely looks like log n. Well, you do analysis with a credit scheme again, and here's what you do. So each internal node stores credits. So if they have 2 children, they store 1 credit. If they have 3 children, they store 0 credits. And if they have 4 children, then they store 3 credits. Okay. So so what you're interested in is saying if I do n of these operations of adding and removing leaves, these should take a total of n time. And you'll argue that by saying, well, for each operation that I do, I will give a small number of credits, not more than 6. And each time I split a node, or each time I merge 2 nodes, I will pay for that with 1 credit. Okay. And if you can do that, then that means that the total number of splits and merges is not more than the total number of credits that you gave out. So if you give out 6 per operation, it won't be more than 6 n splits and merges. And I'll just quickly show you how the credits move around, but I mean we've sort of seen what happens. If I have to do a split, so a split happens because I had something that had 4 children and now it has 5, but because it had 4 children, it was storing 3 credits. So it's got 3 credits sitting on it. And when I do that split, that ends up looking like this. So one of the credits here I will use to pay for the split. That still leaves me with 2. The split produces a node of degree with 3 children. 3 children doesn't need any credits, and this needs a credit because it has 2 children. So I put one of the credits here. Okay. So actually, I can even do better, I guess. So I'll pay 2 credits for this. 2 credits for doing the split. All right. And so splitting only happens at things that had degree 4 before I did anything. and each one of those can pay 2 credits for the split and also maintain the credit invariant. Use the extra one to maintain the credit invariant. So the other thing that happens is sometimes you take a node and one of its children, it has degree 2, one of its children goes away, and you need to, well, you fix that in one of 2 ways. One of them is borrowing. So borrowing is kind of good for us. So this had degree 2, so it had 1 credit. And this had degree 3 or 4. It doesn't actually matter. But let's say that the borrow is successful. So I do that. This borrows the child. And now the point here is, well, that's it. The operation is done now. So if you successfully borrow from your sibling, you're done. You don't need to do any more. It stops here. You've restored all of the invariants. So that only happens once at the end of the operation. And yes, you may need to hand out some credits now. In particular, you may need to hand this thing a credit because its number of children dropped from 3 to 2, but you only have to do that once at the end of the operation. So these don't trickle up. And then finally, the thing that does trickle up is when this happens. So this child goes away, and you need to do a merge. So this used to have 2 children, so it has 1 credit. This has 2 children, so it has 1 credit. You're going to do this merge operation, and they join into one thing that has 1, 2, 3 children. This doesn't need any credits. That's the rule for 3 children. So both of those 2 credits can be used to pay for the merge. And so what's happening now is, and so how much do I have to give out? Well, if you check the rules, you'll see that actually it's only somehow the last step in each operation in which you have to give out credits. And the worst thing that could happen is in that last step, you went from a node that had 3 children, it had 0 credits, now it has 4 children, so you have to give it 3 credits. But that only happens, that's one thing. All right, so at each operation, you give out at most 3 credits, and each time you do a split or a merge, you pay for it with 2 credits. So if you do n operations, you only do 3n over 2 splits or merges. That's the analysis. And so, yeah, so if you do n of these operations of adding and removing a leaf, the real work, the work that's non-constant is the splits and merges, and this shows that the total number of those is only 3n over 2. Okay. Don't worry if you didn't follow that too carefully. It's not critical. The important thing is summarized here, that it basically takes constant time to add or remove a leaf. All right, so now comes the Queap. What's a Queap? It's a 2-4 tree, T plus a list, L. If you look at the leaves of the tree in left to right order, followed by the nodes in the list in left to right order, this is the order that these things were inserted. Okay, so this one here is the oldest thing in the queue, in the Queap. Okay, so its Q number is 0. This one has Q number 1, this one has Q number 2, this one has Q number 3, right? Q number 3 because there are 3 things in here that were inserted before it, but are still there. And all the way up to the last one here, which has whatever, Q number n, if there, n minus 1 if there's n things in the list, okay? So far, that just looks like a queue. And indeed, when you add things, they're just going to go onto the end of this list here. All right. And we need more than that, of course. So this 2-4 tree is kind of a special beast. So I just said what goes in the leaves. What goes in these other nodes? I don't know. Hard to draw a big example of it. What goes in these other nodes? So each node will store, well, 2 things. There's 2 kinds of nodes. These ones here, this is called the left wall. They're special. We'll deal with them in a second. And then there's these other nodes that are not so special. They do the obvious thing. A node like this stores a pointer to the smallest leaf in its subtree. So it stores the minimum value of all the leaves in its subtree. This one too. And well, there's a problem there, and then maybe you know, something like that. Okay, so this is just the min in the subtree. These ones do something really strange. Each of these stores the minimum value not in the subtree. Okay, so for instance, this thing here stores a pointer to the minimum value in the tree other than possibly itself. So it'll be something like, I don't know, maybe that's the minimum overall. This one also stores a pointer to the minimum value that is not in this subtree. So actually, maybe it's better to do an example like this. Okay, so this one is basically the minimum value overall. Maybe it's there. This one is the minimum value not in its subtree. So in this case, it's not going to point to the minimum value overall because that is in its subtree. It's going to point to something outside of its subtree, the smallest one over here, which actually has to be that one there. Okay, so these things here, they point to the min value not in subtree. Now, this node is kind of special because according to heap order, it's the one that should come out, or not heap order, according to queue order, it's the one that should come out next. So that means that if it is the one that comes out next, we need to get to it in constant time. So we'll keep a pointer to that. Keep a pointer to the leftmost node in this tree. It's not the smallest value necessarily. It's just the oldest value. All right. That's good. And well, then we've got this guy, this list, and for that, we do something similar, which is we just keep a pointer to the smallest value in the list. Now, we saw that that's not going to work out great for us overall, so if we resort to dealing with this, we're going to have to do something destructive, but we'll do that. Okay. So we have these three operations we want to do. So maybe the first one, as always, should be find min. So how do we find the min? What's that? We just follow the min pointer. This min pointer? Okay, so this tells us the minimum value in the list. Well, no, these things are disjoint. This is the newest, sorry, the oldest elements, and over here are the newest elements. There's not the same values stored in each of these things. Yep.
You can check the oldest element and see where that's pointing to.
Mm-hmm.
Compare those two, and then also compare that one with the minimum in L.
Yeah. Right. So we have a pointer to the oldest element. So we basically have three candidates. The minimum value could be the oldest element. Or if it's not the oldest element, well, this guy's min pointer points to the smallest value in the entire subtree, except possibly this, which is the smallest value of everything else in the tree. And so it's either this, or it's this, or it's this. Okay. And find min just says we have to tell you what it is. We don't have to do anything after that. So we have to look at three values and then return the minimum of the three. Okay. So find min. It's either the min L or oldest or the min of the oldest. So that we can definitely do in constant time. All right, good. Let's try another one. Add must be simple because it has to run in constant time, so we should be easy to do. All right, so we want to add something. We know that we're storing the elements from left to right in this picture, oldest to newest. So where do we add it? You know, the new thing is that we're adding is the newest thing. So we add it here. This is the newest thing now. Anything else we need to do? What's that? Not yet. Not necessary to do that yet. Yeah. We need to check if this new value that we inserted, maybe it's smaller than the smallest value in the list, in which case we update the min L pointer to point to it. Really easy. Really trivial. So only one operation left to do. Remove min. Well, there's very naturally two different cases to consider. So we know how to find the min, so we know where the thing is that we have to remove. And it's either going to be in this tree, or it's going to be in this list. So let's look at the first case where it's in this tree. All right. So well, the easiest thing is if we get really lucky, the oldest thing is the minimum thing. Okay. In which case, what do we have to do? We remove it. That takes constant amortized time. That's what we argued about 2-4 trees. So we remove it from the 2-4 tree. No pointer to update there. And furthermore, this thing is on this left side here. So none of its ancestors needs to have their min value updated, because the things on this left wall, they are not pointing to the minimum below them in their subtree, they're pointing to the minimum outside the subtree. So removing something from the subtree below them they don't have to be updated because of that. Okay. So that's the really easy case. The trickier case is, well, when you have this picture just like this, that this is not the min. The min is something over here. Okay. So we're going to have to cut that out. And what do we, so we remove it. What needs to be updated? Well, everybody who is, well, I mean, everybody here is storing some min value either in their subtree or outside their subtree. So we need to update the ones that need to be updated. So in particular, everything on this path may need to be updated. In fact, it definitely needs to be updated, because the smallest value in this subtree just disappeared. Okay. Then there's also this path. Okay. Because each of these points to the smallest thing not in their subtree, and indeed this was the smallest thing not in their subtree. In fact, it's the smallest thing overall except for in fact, it's definitely the smallest thing overall. That's why we're removing it. So all of these need to be updated. Okay. So, well, it's kind of easy to update each one of these because each one of these has 2, 3, or 4 children, and the minimum in its subtree is just the minimum. You look at those 2, 3, or 4 children and take the minimum. That tells you the minimum in the whole subtree. And so you do that for this one, and then this one, and this one, and this one. So that takes constant time for each of these things to update the mins along here. Now you have these things. You want them to be updated as well. And each of them, so this should be the minimum not in your subtree. So actually for this one, you don't have to do anything because it's pointing to something outside of there. The thing that you touched was in its subtree. For this one is when the action starts, because this was definitely pointing to this before. Now we need to know the new minimum not in the subtree. Where is that? Well, that new minimum not in this one subtree is either the minimum not in this subtree, or it's the minimum here, right? And that's everything else. Everything outside of this subtree is exactly that, which is captured by here. That's everything down there, and here's everything outside of there. Okay. Well, can be a couple of these. There can be 3 of these. So that's how you update this one. And now, well, now you just walk. I mean, you do the same thing here, the same thing here, the same thing here, and so on. Okay. So how long does that take? Well, that takes time that's proportional to the length of that path. Okay, well, we need it to take time that's proportional to the logarithm of the Q number of the thing that we're removing. Well, what is the Q number of the thing that we're removing? It's actually the number of leaves here. This thing here is Q number of the minimum. So if this height here is h, we need to argue that the Q number is something like 2 to the h. Is it? Well, it definitely is. Why? Because if this is height h, then this is height h minus 1. This node here is the root of a 2-4 tree of height h minus 1. So that means that there are 2 to the h minus 1 leaves here, at least. So the remove min time runs in O of h time, and the Q number of the min is bigger than or equal to 2 to the h minus 1, which means that the log of the Q number of the min is bigger than or equal to h minus 1. And so O of h time is, well, is fast enough. Okay. So we need to run in O of log of the Q number of the min time, and we do that. All right. So that's the first case, is when it is in the tree, runs in O of log of the Q number of the min time. The second case is when it's in the list here. And to handle that, we're going to do something extremely destructive or constructive, depending on how you look at it. We're going to take everything from the list and put it in the tree. So what's that going to look like? We had a picture like this before, and that's going to go to a picture like this, where this is the stuff that was in the list. It's going to be over here on the right part of this tree. All right, so here's L items that I need to put in the I need to add to this tree. So that's going to take, well, the time is going to be O of L, just to take all of these list items and make them leaves in the tree. Then that creates a whole bunch of new internal nodes. But the number of new internal nodes here is only proportional to the number of leaves. So O of L, to compute the mins of all these values, these new internal nodes that you created, you can just do that bottom up. So that's all captured in the O of L. But what else happens? What else needs to be updated? Possibly, and also any of these things here. Right? These things here, they all have new stuff added in their subtree, so you need to update that. And then all of these things here, because they all have new stuff added not in their subtree, so you need to update those if necessary. Now, how much is that? Well, the thing that we deleted, the min was somewhere inside this list. Maybe it was at the front, maybe it was at the back, it doesn't matter. But that means everything that was in the tree before this is older than the thing we're deleting. Okay, so this number of things here, this is the Q number of the min is at least this big. Okay, and now you can just check, and it's sort of two things to look at. One is the tree is small and the list is huge, where you get a picture then that looks like this. Right, there's the list stuff, and it actually dominates most of it. Or the tree is small and the tree is large and the list is small, and in which case you get a picture like this. So in this case, it's not a problem because you had to do, I mean, you filled in all of this, which is just proportional to the length of the list. And then this thing is tiny. This is just a log of whatever, log of that. So that it's going to be dominated by the size of the list. And for this one, it's also okay because, well, what you had to do was this whole path and part of this path to do these updates. But the length of this path is about, I mean, it's log of the number of nodes leaves in the tree before you added the list, which is log of the Q number at least. I mean, it's like log of the Q number. All right, so log of Q min. All right, so list is big, then it's dominated by this O of L. List is small, like for instance, the list might only have one element in it, in which case you're basically just adding one leaf here and updating all of these, but that's okay because it's log of the Q number. Okay, all right, but there's something wrong here because of this. We said we want remove min to run in time proportional to the logarithm of the Q number of the min, but it runs in some weird time that includes this L in it. Okay, that's not great, or it's not what we want. So we need some way to argue about that. And we can't, as usual, sometimes L gets long, because the min is never in L for a long, long time, and then suddenly you have to merge a giant thing. So I mean, this is not some fake thing that's wrong with our analysis. It's definitely true, but we need to argue that if we do many operations, that on average this should be a constant. And for that, there's a really easy credit scheme. Remember when I added something, I stuck it on the end of L. So when I do that, I can just put a credit on it. And I won't touch that credit until that thing gets put into the tree. So that means that every item in L has a credit on it. And when I merge the list into the tree, when I'm forced to do that, they all pony up and pay their credit. And that means they give L credits, which is enough to pay for this part of the running time of the merge operation. Okay. So again, I only give those things out, one credit out each time I add something. So that means if I do a total of n operations, I don't give out more than n credits, which means that the total time I spend merging these lists into these trees is only proportional to n. Okay. So constant per operation on average. All right, so that's it. Clever combination of tricks, good use of data structures to engineer this thing that has what's called the queue-ish property. It's a priority queue that performs well when the remove min operation is somehow close to what you would get from the normal queue remove next operation. All right, and that's our time for today. Yeah. When will what? Yeah. So when you remove the oldest element, what's the new oldest element? It's just the sibling of that.
If that's the one, the previous oldest is like
Well, there is nobody, there's never anything pointing to this.
I mean, the previous oldest was pointing to the smallest, the everything other than
No, so right, so each of these things here is pointing to the smallest thing not in their subtree, which means they could be pointing, like this guy could be pointing to this one or to something far away, but there's nothing, when I remove this smallest one, nobody was pointing to it. Yeah, because all its ancestors are on the left wall and all of them point to something outside their subtree. Oh, this one here? Yeah, so it should point to the smallest thing outside its, I mean, yeah, outside its subtree. So that doesn't change. Yeah, the smallest thing to the right of it, I guess. So that doesn't change.
This one is not like on the left wall, so.
Which one? This one here?
Yeah.
Well, it is now.
Oh, no.
Yeah. So, and in fact, it can get its. Yeah. So after you delete this, so it now needs to point to the smallest thing outside its subtree, which it can get from, that'll be this either one of its siblings or the smallest thing outside this subtree. So you look at your siblings, maybe it's one of them. If not, it's the smallest thing over here. So in general, in all of these things, finding that whether it's in your subtree or outside your subtree, you can either get it from looking at your children, up to 4 of them, or looking at, for outside your subtree, looking at your siblings and your parent. That covers the whole thing. Okay. So it's a really clever combination of techniques. In particular, I really like this treating the left wall separately. It's an elegant trick. All right, so thank you. Enjoy the rest of your week.